Okay, so for this unit is on our exponents and roots unit. That is basically that concept or idea of what we call real numbers. So this idea of real numbers means that it's all natural, whole, integer, rationals, irrational values. If you notice, irrational is a value that's set off aside. It's completely isolated from the rest of the different types of real numbers. And then if you notice with the rational numbers is incorporating all of integers, and integers incorporates all of whole numbers, and whole numbers incorporates all of natural numbers. So if something is rational, it means it is also integer. It is also, not rational. If something is natural, if it's a natural number, it means it's also a whole number. It's also considered to be an integer. It's also considered to be rational. Okay, so it builds into itself. Now, not every single rational number is an integer. Not every integer is whole. Not every whole number is natural. So we're going to learn which values are considered to be what. So we're going to start with natural numbers. And the concept or idea of natural numbers are basically values that start at 1 and then continue counting up. So 1, 2, 3, 4, all the way up to infinity. Okay, natural numbers go on forever and ever and ever. They never stop. Now, whole numbers is also going to include 1, 2, 3, 4, but it has one other addition. Who can tell me what the other addition is going to be? Well, no, remember, it keeps counting on up. So yeah, natural numbers are also 5, 6, 7, 8. Keeps going on to positive, or to all of infinity. So obviously I'm counting 1, 2, 3, 4 all into infinity, but there's one other value that I'm including in a whole number. Anybody know? What do you think, Jesse? 0. Very good. The value 0. So natural numbers starts at 1. Whole numbers starts at 0. 0 is considered to be a whole number, but not a natural number. So 0 and all the natural numbers are also called whole numbers. Now, with integers, again, we can include, 0. We can include 1, 2, 3, 4, 5, and it can keep going on and on and on all the way to positive infinity. But there's another addition into the integers. What other numbers fall into the integer category? Somebody said it. What? Negatives. Very good. Negative. So I can have -1, I can have -2, -3, all the way to negative infinity. Okay, so infinity means that it just keeps going on forever. We do not know what the largest number in the entire world is or what the smallest number in the entire world is. It's infinite. They never stop counting. So integers are all whole values, both positive and its negative counterpart or its opposite. And then it includes that neutral number, 0. Rational numbers. With rational numbers, again, we are including all the natural numbers. So, a 1 and a 17, those are considered to be rational. We're including all the whole numbers. So 1, 17, 0, 0 is also included as a rational. Our integer values, okay, so 1, 17, 0, a -5, a negative, 200. Those are all considered to be rational numbers, but there's an addition to it as well. Rational numbers can also be fractions and decimals, as long as their decimal form repeats. So like 0.3 repeated, or it terminates like 0.7. Okay, so as a fraction, 1/2. 1/2 is a rational number because when I change it to a decimal, 1/2 is 0.5. 0.5 is a terminating decimal. Okay, if I write -7 and 4/9, -7 and 4/9 is also considered to be a rational number, because as a decimal, it's negative 7.4 repeated. The 4 would repeat. So the important thing about rational numbers, what you need to make sure you keep in mind with rational numbers, as a decimal, it repeats or terminates. It repeats or terminates when it's in its decimal form. That's the important thing about being a rational number. So rational numbers are our natural numbers. Rational numbers are our whole numbers. Rational numbers are also our integers, but rational numbers has one extra special thing about them. They can also be decimals and fractions as long as they repeat or terminate. So then off to the side, irrational. So if rational means in decimal form it repeats or terminates, irrational means in decimal form it does not repeat and it does not terminate. It is a value that goes on forever. It never stops, never ceases. Who can tell me what is the most famous irrational number that we just dealt with last unit? Nathan? Pi. Pi is our most famous irrational number. It is a value, even though we used it as 3.14, it is a number that goes on forever, and there is no pattern. There's no rhyme or reason to how it goes. Okay? So as a fraction, that would be 22 over 7. 22 over 7 is an irrational value that goes on forever. It has no repetition. It has no pattern. And then something else, we call them radicals or non-perfect squares. So like the square root of 30. The square root of 30 is an irrational value, because when we take the square root of 30, and here I'll show you in a calculator, square root of 30, when I type it in, it's just going to keep going on, and I don't know what is the next value on here on my calculator. All I know is that my calculator is a finite tool. My calculator has to stop, but the value itself just keeps going on. Okay? And there's no pattern. We don't know what the next number is going to be. Okay? So those are our irrational numbers, and we'll write that up off to the side. Irrational. It does not repeat or terminate. Okay? It does not repeat. It does not terminate. It has no ending to it. So what we're going to do now is we're going to go ahead and take a look at a couple of problems below, and we're going to identify what set of real numbers does that value belong to. So if it's a natural number, then it means it's also whole, it's also integer, it's also rational. Okay? Because natural fits inside of those things. So anything that it's inside of is also what category it would belong to. So let's take a look here. Always the first question you should ask yourself if you're trying to identify what set it belongs to, ask yourself the question first, is it a natural number? Is this value here, this 0.252525, and it's just going to keep going, is that considered to be a natural number? Yes or no? No. Right? Natural numbers are whole values. There's no decimal to it. Okay, so this is not a natural number. So what about a whole number? Is this a whole number? No. Okay, because again, whole numbers starts at 0 and continues going up in increments of 1. What about an integer? Is it an integer? No. Okay, integers are 0 in all positive values and their opposites, those negative values. Again, this is a decimal. So now we ask ourselves, is it rational or is it irrational? So remember, rational means it will repeat the same value over and over and over again. Does this repeat the same sequence of values over and over and over again? Yeah. 2, 5, 2, 5, 2, 5, 2, 5, 2, 5. It's going to keep going on and on and on. So this is considered to be rational. That's all we have to put down. Okay, for problem number 2. Problem number 2, the value 0. Again, we're going to start with natural numbers. Is 0 a natural number? No. What about a whole number? Yes, right? 0 falls in the whole number category, so I'm going to go ahead and write that down. This is a whole number. And since it's a whole number, what else does it make it? An integer. Very good. And rational. Good. It makes it an integer and it makes it rational. So it has all those categories that it's going to belong to. Okay, I want you guys to try problem 3 and 4 on your own. Okay, let's go ahead and go over this. Square root of 3. What category does square root of 3 belong under? Irrational. Very good. It is going to come out to a decimal value that does not repeat. It does not terminate. It just keeps going on forever with no rhyme or reason, so it's an irrational number. What about problem number 4? Rational and integer. Very good. If you were to go ahead and simplify that, if you type negative square root of 16 into your calculator, it's going to come out to negative 4. And negative 4 happens to be an integer value, and it's also an not irrational, a rational number. So it's an integer and it's rational. Integer and rational. Okay, so speaking of those square roots, roots have what we call radical signs. So that root sign is called a radical sign, and what goes inside of it, so like the 16 or the 3 or the 30, those are called radicands. Those are the values that reside inside of it. And how a root works is you're trying to identify, so if it's a square root, you're trying to identify what times itself will equal the radicand. So for example, if I say the square root of 25, the square root of 25 is going to equal 5 because 5 times 5 is equal to 25. We're looking for what value times itself is going to equal that radicand value. It's also going to equal negative 5 because negative 5 times negative 5 will also equal a positive 25. So your root, your square root has 2 solutions to it. 2 solutions, the positive solution and a negative solution. For problem 4, the only solution we could have was a negative solution because it's indicating that it only wants the negative solution there. Okay? Go ahead and flip it on over to the back. So what we're doing here is we're taking a look and we're trying to identify what times itself is going to equal 100. What value times itself will equal 100? Michaela? 10. So when I simplify, when I say square root of 100, the square root of 100 is going to be 10, but it could also be negative 10, can't it? Because negative 10 times negative 10 will also equal 100. Christian, head up. Thank you. So what we do is we put a positive and a negative sign in front of it. That indicates that we're dealing with both positive and negative 10s. Again, because 10 times 10 equals 100, and negative 10 times negative 10 is equal to 100. Okay, so our solution is both positive and negative 10. For problem 2, the only solution can be what? Negative 5. The only solution could be a -5 because of the fact that we have that negative sign on the outside. That's the only solution it could possibly be. I want you guys to go ahead and do problems 3 and 4. Just do 3 and 4. We'll do 5 together. Just do problems 3 and 4. We'll do problem 5 together. Okay, so let's go ahead and go over problem number 3. The square root of 1.21. What is that going to come out to? Hasaifa? Good. Positive and negative 1.1. Jesse and Chisindi, head up, please. Thank you. Okay, you're going to get a positive and a negative 1.1. It's not going to show up on your calculator as a negative. It's only going to show up as a positive. You have to know that it could be both, that it could also be a negative 1.1. Again, because 1.1 times 1.1 will equal 1.21, but also negative 1.1 times negative 1.1 is going to equal 1.21. Okay, what about the square root of 36 over 169? What is that going to come out to? Noman?
6 over 13.
Good, 6 over 13, but don't forget positive and negative. It can be both. Okay, if you were to just do this by hand, the square root of 36 is going to come out to 6, and the square root of 169 comes out to the 13. Okay, but we know that it's going to be a positive and a negative, so we need to make sure we do both positive and negative 6 over 13. Okay? All right, and then here, I didn't want you guys doing this one on your own. A square root of 30. For a square root of 30, so with a square root of 30, there's two different ways that they can ask you to work this out. They can either ask you to find the value and round it to the nearest, whole number, or nearest tenth, or nearest hundredth, or they might ask you to estimate it by finding the two perfect squares that it falls between. So what that means, if it's not perfect, so this is not a perfect square, nothing times itself is going to equal 30 that we know of, that no whole number that we know of. So we call it not a perfect square. So what we want to do is we want to identify the perfect squares that it can fall between. We're going to find the two perfect squares that it falls between. Okay, so let's start from the beginning. We know what 1 times 1 is. What is 1 times 1? 1. What's 2 times 2? 4. 3 times 3? 9. 4 times 4? 16. Okay, we could probably still go. What about 5 times 5? 25. 6 times 6? 36. Okay, so 25 is lower than 30. 36 is higher than 30. So there's our two perfect squares that we found. Okay, square root of 25 and square root of 36 are the two perfect squares that surround that square root of 30. So what I want to do is I want to figure out, okay, which one of these perfect squares is 30 closer to? Is 30 closer to 25 or closer to 36? 25, right? It's only 5 units away from 25. It's 6 units away from 36. So it's a little bit closer to that square root of 25. So what we'll do is we're going to estimate it to being roughly about 5. Okay, I'm going to write that down. It's closer to the square root of 25. So it's approximately 5, plus or minus. We don't know whether it will be positive or negative because it does not indicate if it wants positive or if it wants negative. So we just put plus or minus 5. Now, if it asked, let's say instead it asks to round. Round to the nearest hundredth. If it's asking us to round to the nearest hundredth, then that's when we would physically find that square root. We would type second, and we would type that x squared button. That x squared button has the square root symbol above it, so everybody should see the square root symbol. You're going to type 30. Then you're either going to hit enter, and then you're going to hit your conversion button. That double arrow button will allow you to convert. And we got 5.4772255575. It just keeps going on. So if I were to estimate it, 5.47722, I want it to the nearest hundredth. The hundredth is that first 7 that I see. That's my 100th place value. So I'm going to look at the number behind it. This number is going to tell me whether I'm going to keep this as a 7 or round it up to an 8. What am I going to do? Keep or round? Round. So we're going to round it. It's going to become 5.48, roughly. Positive and negative. Okay? So these are the two different things that they might ask you to do. They might ask you to identify the two perfect squares that it surrounds, or they might ask you to estimate it to a nearest place value. Okay, go ahead and do 6, 7, and 8 on your own. Do problem 6, 7, and 8 on your own. All right, let's go through this quickly. The square root of 225 over 625, what is that going to come out to? Go ahead, Josefa. Positive and negative 3 over 5. You should get positive and negative 3 over 5. Okay, what about the negative square root of 400, Alan? Negative 20, and that's the only one that we would want because it indicates that it wants it to just be the negative. Okay, that negative sign in front means it only wants the negative answer. And then here for problem number 8, I'm just going to go ahead and say to round to the nearest hundredth. We'll round to the nearest hundredth. Approximate the 100th place value. So if we do the square root of 54 and we estimate it to the nearest hundredth, what is that going to come out to? Navilkis?
100?
Huh?
100?
Not 100, no. If you take the square root of 54 in your calculator, okay? Somebody besides Josefa. Michaela? 7.35, positive and negative. So we estimate it, it's going to come out to both positive and negative 7.35. Okay? All right, let's go on to the next page. So square roots aren't the only thing that you're going to be solving for. Sometimes you might be solving for a cubed root. Shasimdi, stand up because you keep falling asleep. Okay, sometimes it might be a cubed root. So like we did on here, if you hit second, if you hit the second button and then you hit the x squared button, it gives you a square root symbol. When you want a cubed root, you need to type 3. So everybody practice this. Type a 3. Then you're going to hit the second button. And then you're going to hit this little itty bitty asterisk arrow, which above that has the x square root symbol. So you're going to hit this little arrow, and notice it now turns the 3 into a small value up in the corner, the left-hand corner. That's not an exponent. It's not an exponent because exponents would be on the right-hand side. This is a root. It's a cubed root. You can take any number and turn it into a root. You have 4th roots, 5th roots, 27th roots. Okay? All a root is an exponent, but it's a fractional exponent. So when I say a cubed root, it's really taking a number and putting it to a 1/3 exponent. When I say taking a square root, it's taking a number and putting it to a 1/2 exponent. Okay? So here is how you create these cubed root symbols. So what we're going to do is we're going to take the cubed root of 125. So when I take cubed root and I type 125 and hit enter, I get a 5. So now let me ask you, do you think it's going to be positive and a negative or just the positive? Both? Okay, let's test it out. So we're saying right now, I'm saying 5 because if I do 5 times 5 times 5, it's going to come out to 125. What is negative 5 times negative 5 times negative 5 equal? Go ahead and do that in your calculator. Do negative 5 times negative 5 times negative 5. What do you get? Negative 125. Is negative 125 the same thing as 125? No, it's not the same thing. So for here, you don't have positive and negative at the same time. You only have positive or you only have negative. So notice we happen to have a negative inside of this radical. We have a negative inside of this cubed root. That's because you can get a negative answer when you multiply a negative times negative times negative. So if I do the cubed root of negative 64, cubed root of negative 64, what is that going to equal? Negative 4. Good. That's because negative 4 times negative 4 times negative 4 equals negative 64. So there's my answer. And then we're going to do the cubed root of this fraction. Cubed root of 216 over 343. Go ahead and type that into your calculator. Do cubed root of 216 over 343. Kennedy, what do we get? Oh, is your calculator not working? Hit the on and clear button at the same time. Can you help her do that? On and clear at the exact same time. Eli, what is your answer? 6 over 7. Very good. Okay, so we get 6 over 7. And again, the way that we do that, let me show you one more time. In order to do it, you're going to hit the number 3. You're going to hit second. Then you're going to hit this little up arrow. And then when we want to type a fraction, we'll hit the fraction button and we'll type 216 over 343 and enter. There we get it, 6 over 7. That's because 6 times 6 times 6 is 216 and 7 times 7 times 7 is 343. Okay? Now, we can also solve equations the same way. One thing that you need to make sure you understand is that the inverse, remember, we solve equations using inverse operations, opposite operations. The inverse of a power or of an exponent is a root. So if my exponent is to the second power, I need to take a second root or a square root. If my exponent is cubed or to the third power, I need to take the cubed root in order to be able to undo it. So I'm going to take the square root of both sides of this equation. When I take the square root of x squared, I just get x. And when I take the square root of 196, I'm going to get either a positive or a negative 14. Same thing for cubed roots. If I have x cubed is equal to 8, I need to take the cubed root of both sides. Not a square root, a cubed root. When I take a cubed root of x cubed, I get just x. When I take a cubed root of 8, I get a positive 2. And again, I can only have it being positive. Now, please also note that a negative on the outside of a square root is not the same thing as a negative on the inside of a square root. Right now, I want you guys to type the square root button, hit second and square root, and I want you to type negative 16 and hit enter. Look what happens. You get an error. The reason you get an error is because that is not a real number. Remember when we talked about real numbers, it never had any display of a negative value inside the square root. It's because there's not a number that you can multiply by itself that's going to give you a negative. Okay, there's not any numbers you can multiply by itself. It's going to give you a negative. So these negatives inside of these square roots are not real. They're called imaginary numbers. These are called imaginary numbers. That is something you'll learn about when you get into algebra. So just like we are talking about real numbers, there is such thing as imaginary numbers as well. All right. Flip it on over. Enough about the roots. Let's go ahead and get into our exponents. Talk about our exponents now. So this value, this 5 to the third power, 5 to the third power, this is your base value. So underneath here, I want you to go ahead and write down that this is a base. And then the number in the corner, that is your exponent. And what the exponent tells us, it tells us how many times we're going to use the base as a repetition of multiplication. Tells how many times the base is used as a factor in multiplication. Okay, when you're multiplying these values over and over and over again, that exponent is telling you how many times to do it. So 5 to the third power originally was 5 times 5 times 5. Right? We take the base and we're multiplying it by itself over and over again 3 whole times. Now when we read these, the way that we read our exponents or our powers is we say it's the base to the blank power, and the blank is the number. Every single value has an exponent. Every number has an exponent. Even if it's not written, it's an imaginary one, or not imaginary, an invisible one. Every single value has an exponent, even if it's not written. So 5 is also known as 5 to the first power. Now, the second power and the third power are a little bit more unique. The reason that they're more unique is because they also have another way that you can write it or speak it. So 5 to the second power is also known as what? Anybody know? 5 squared. Good. 5 squared. It has its own little unique phrase, and we tend to say 5 squared more often than we say 5 to the second. 5 to the third also has a unique one. What is that called? 5 cubed. Okay, so 5 to the third power would be known as 5 cubed. And that's the only two that have their unique little phrases. Once we get on, it just continues to be blank power. So the 4th power, the 5th power, the 6th power, and so on and so forth. Okay, now standard form. Standard form is also known as expanded form. Expanded form, meaning over and over multiplication. So if I say 6 times 6 times 6 times 6, that is standard form or expanded form. In exponential form, it would be 6 to what power? To the 4th. 6 to the 4th power would be 6 times 6 times 6 times 6. Okay, so let's go ahead and take a look at problem number 1. Problem number 1, we have 4 times 4 times 4 times 4 times 4. When I want to write that in exponential form, my base is 4, my exponent is what? 5. So we have 4 to the 5th power. For problem 2, we have 3 times 6 times 3 times 6 times 6. So I have several bases. I have 3 as a base, and what would the exponent be? How many 3's do I have? 2. So it'd be 3 squared, or 3 to the second power. And then I also have these 6's. 6, 6, and 6. So it's 6 to what power? The third. 6 cubed. Christian, make sure you're keeping your hands to yourself, please. Okay. Here for problem 3, I've got -2 times -2 times -2. What's important is to make sure that I keep that -2 inside of parentheses and then write my exponent being a 3. If I don't write it inside parentheses, it could potentially change the answer. Let me show you what I mean. -4 to the second power without parentheses is not the same thing as -4 to the second power with parentheses. -4 to the second power without the parentheses means you're doing -4 times 4. And 4 times 4 is 16, so you'd have -16. -4 in the parentheses to the second power means you're doing -4 times -4, which would come out to a positive 16. Those are not the same. They're not equal. So those parentheses can change your answer. Same thing with fractions. When you're doing this with a fraction, you must make sure you put the fraction in parentheses before you write your exponent. Because if you don't, 2 to the third power over 3 is what it would look like. 2/3 to the third power without the parentheses means you would be doing 2 times 2 times 2 over 3. That's not the same thing as 2/3 times 2/3 times 2/3. Okay, real quickly, go to the next page. We are almost done. Okay, so we have -5 in parentheses raised to the fourth power. That means I am repeating my -5 times -5 times -5 times -5. When I multiply that over and over and over again, I get positive 625. If I did not include my parentheses, I would wind up getting a negative 625. Those are not the same thing. For problem 2, this means I'm doing 6 over 7 times 6 over 7. That's going to come out to 36 over 49, which is different if I didn't have parentheses. When I don't have parentheses, that is 6 times 6 over 7, which would be 36 over 7 as my answer. Very different answers here. Okay, and then for my last problem, I know that we're getting ready to go. For the last problem, it says a squared plus b squared, where a is equal to -3. So I'm going to do -3 in parentheses and then square it. -3 squared comes out to a positive 9. Then I'm going to do b is equal to 5. So that means I'm going to do 5 squared. What's wrong? We're going to do 5 squared, and 5 squared is going to come out to 25. And then we would just add 9 plus 25 together, and we would get 34 as our final answer. Okay, go ahead and pack up.